and a total graph of some standard graph. These are the outline of my presentation. Introduction, sum non sum divisor Codial graph, sum non sum divisor Codial graph, main results and references. Graph leveling, the definition of graph leveling. If the vertices or edges or both of the graphs are assigned values subject to the certain condition, which is known as graph leveling, which was introduced by Rosa in 1960. A dynamic survey of graph leveling, which is published and updated every year in Electronic Journal of Combinatorics by the mathematician Joseph Hegelian, is the huge source of the literature in the field of graph leveling. The below is the reference for this one. This is the definition of divisor Codial leveling. A graph G with vertex set VG star and edge set EG star be a simple graph. A function Xi from VG star to 1 to up to cardinality of VG be a bijection function. The induced function Xi star from EG star to 0, 1 is defined by Xi star of E equal to RF is 1 if Xi of R divides Xi of S or Xi of S divides Xi of R, otherwise 0. Which is if the function satisfies the condition, total number of edges having level 0 and the total number of edges having level 1 differ by at most 1, then this graph, which is known as divisor Codial graph. The concept of the divisor Codial leveling, which was introduced by Bharatha Rajan, Navneet Krishnan and Nagarjun in 2012. This is the example of divisor Codial leveling graph, and a wheel graph, which is a divisor Codial. Vaidya and Shah prove the following graphs are divisor Codial: helm, flower, gear, splitting graph of star, degree splitting of bistar, shadow graph of bistar. Bosome and Kanani prove the following graphs are divisor Codial graph: bistar, splitting graph, degree splitting of bistar, shadow graph, barycentric subdivision of bistar, and restricted square of bistar. Adalja and Khodasra prove that the following graphs are divisor Codial graph. Switching of vertex except apex vertex in gear cell flower, switching of pendant in star graph, switching of any vertex in complete bipartite K2n and K3n, duplication of any arbitrary vertex as well as any arbitrary edge in star, duplication of vertex by edge and edge by vertex in star. Khodasra and Adalja also prove the following graphs are divisor Codial graph. This is the definition of some divisor Codial leveling. A bijection Xi from VG star to 0, 1 to cardinality of VG star is called a sum divisor Codial leveling of G. If the induced leveling function Xi star from EG star to 0, 1 defined as Xi star of E equal to RS is 1, if 2 divides Xi of R plus Xi of S, otherwise it is 0. Satisfies the condition, total number of edges having level 0 and having level 1 differ by at most 1. A graph which admits a sum divisor Codial leveling, which is known as sum divisor Codial graph. The concept of sum divisor Codial leveling was introduced by Lord Swami and F. Patrick in 2016. This is the example of sum divisor Codial leveling, any star graph, which is a sum divisor Codial graph. If we denote apex vertex by 1 and all the remaining pendant vertices by any level, that means 2, 3, 4, 5, 6 in any sequence, then this graph becomes sum divisor Codial graph. This two graph leveling technique, divisor Codial and sum divisor Codial leveling, behave independently. This fact is exemplified in the following examples. Star graph K1 is both divisor Codial as well as sum divisor Codial. Corona graph of K2n with K1 is a divisor Codial for every n, but it is not sum divisor Codial for n congruent to 0 mod 4. The triangular snake P6, which is not divisor Codial, but it is a sum divisor Codial. And complete graph Kn with vertices greater than or equal to 7, which is neither divisor Codial nor sum divisor Codial. Some non-sum divisor Codial graphs, Lord Swami and F. Patrick prove the following graphs are sum divisor Codial. In another paper, Lord Swami and F. Patrick also prove the following graphs are sum divisor Codial. Adalja and Khodasra also prove the following graphs are sum divisor Codial. Switching of a vertex in cycle, switching of a vertex in cycle with one code twin code triangle, and switching of a vertex in crown and armed crown. Some known sum divisor Codial graphs. In another paper, Adalja and Khoras have proved that the following graphs are sum divisor Codial: bi-star, splitting of bi-star, division splitting of bi-star, shadow of bi-star, restricted square of bi-star, barycentric subdivision of bi-star, and corona graph, corona product of bi-star with K1n, where in bi-star graph, M and N both are distinct. This is the main definition for this presentation. Middle graph. Middle graph of G is the graph whose vertex set is union of vertices and edges of graph G, and in which two vertices are adjacent. If and only if either they are adjacent edges of G, or one is the vertex of G and another is an edge incident with it. This is the example of middle graph of a path having vertices 5, V1, V3, V5, V7, V9, and V11, which are the vertices of main path graph, V2, V4, V6, and up to V10, which are the newly added vertices. So we have one edge between V1 and V3. So now we need to add the vertex corresponding to this edge, and now we need to join V1 and V2, V2 and V3. Similarly for the remaining all the vertices, and after that we need to join all the newly added vertices. So the resulting graph, which is known as middle graph of path. So this is another main definition for this presentation, which is total graph of G. The total graph of G of the graph whose vertex set is V of G and union U of G, edge of G, and in which two vertices are adjacent whenever they are neither adjacent or incident in G. In the previous definition, they are not incident, they are only adjacent, but while in this one, if it is incident, then we need to join that one also. That means this is the main cycle, V1, V2, V3, V4, V1, V3, odd vertices, the vertices having odd number, V1, V3, V5, V7, V9, and V11, which is the main cycle. And the vertices having odd number, which is the newly added vertices, V2, V4, V6, V8, V10, and V12. So this is the graph of total graph of the cycle having vertex 6. Yes, this is my main result to this presentation. The graph, middle graph of path is a sum divisor Codial. I didn't include the detailed proof right now. Just I use the particular example at here, and I already submit detailed proof in the presentation in my research paper. Yes. So just I consider the example of this one. Here V1, V3, V5, V7, V9, and V11, which are the vertices of the main graph, and V4, V2, V4, V6, V8, and V10, which are the newly added vertices. If we label the vertex V1, and for the newly added vertices, if we use 3, 2, 4, 5, 7, 6, 8, 9, 11 in such a way, and after that, if we use the next number to this last vertex of the path, and in a sequence, we will use the remaining labels in a sequence, then the resulting graph satisfies the condition for the sum divisor Codial labeling, and which is a sum divisor Codial graph. Second example, a middle graph of cycle is sum divisor Codial graph, except for n congruent to 2 more 4. This is the example of middle graph of cycle having vertices 5, V2, V4, V6, V8, and V10, which are the vertices of the main cycle, and V1, V3, V7, V9, which are the newly added vertices. If we use the label to the newly added vertices in such a way that 1, 3, 2, 4, 5, 7, 6, 8, up to so on, and if we use 6 to the last, last number to the last level, and then after we will use the remaining labels in a sequence to the remaining vertices 7, 8, 9, 10, up to so on, then this graph becomes sum divisor Codial graph. Middle graph of star graph, which is a sum divisor Codial graph. This is the example of middle graph of star. V0, which is the apex vertex, V2, V4, V6, V8, and V10, which are the pendant vertices of star. V1, V3, V5, V7, and V9, which are the newly added vertices. If we label the V0 vertex to 1, then newly added vertices with 3, 2, 4, 5, 7, 6, 8, and up to so on. And for the remaining vertices, If we use the remaining label to the remaining vertices, then this graph becomes sum divisor Codial graph. Similarly, we have 3 more results for total graph. So
Divya, you have come to the end of the time.
Yes,
Please
yes.
reframe your presentation.
Yes. A total graph of path, which is the divisor Codial graph. This is the example of total graph which satisfy all the conditions. Next result, that is the total graph of cycle. One example of total graph of cycle, and we have one more result. This one is the last result. Total graph of star, which is a sum divisor Codial graph. This is the example of total graph of star. This is the conclusion. In this paper, in this presentation, we have shown that middle graph of path, cycle, and star, as well as total graph of path, cycle, and star, which are the sum divisor Codial graph. A similar investigation can be carried out for the some other graph families. These are the references.
Any questions? Okay. Thank you, Divya.
Thank you, sir.
Yes. Now we are going to the next participant, Anjana TS. Paper presentation number C02. Anjana, am I audible?
Yes, sir. Yes, sir. Am I audible, sir?
Yes. Now you can share your screen.
Is my screen visible, sir?
Your time starts now.
Okay. Good afternoon to all the dignitaries present there. Today, I, Anjana TS from Amrita School of Arts and Sciences, Kochi, would like to present my paper titled A Super Domination Number of Cycle-Based Graphs and Components of Graph. So here mainly we consider simple connected undirected graphs having V as the vertex set and E as the edge set. A set which is a subset of the vertex set S is said to be a super dominating set if for all vertex in the S bar X complement there will exist a U which will be there in S such that the neighborhood of U intersection S bar is a single element V, where S bar is equal to V if set difference S. And the least cardinality among all the super dominating sets in G is the super domination number, which is denoted by gamma ST of G. Suppose there are two connected graphs G and R, and we have a vertex C which is of the graph R, then the component of the graphs G and R is a graph which is obtained by taking one copy of G and cardinality V of G copies of R, and we identify the jth copy of the graph R at vertex C with the jth vertex of G. Here we mainly analyze the super domination number of cycle-based graphs and component of graphs, and the relationship between domination number and super domination number of component of graphs. So a graph is a basic definition is that it consists of a pair V comma E, where V is a non-empty finite set whose elements are called vertices, and E is a non-empty finite set of unordered pairs of distinct elements of V which are called as the edges. Our objective is to find the super domination number of flower graph and friendship graph, and to obtain the component of some graphs, to obtain the super domination number of component of graphs, and also to obtain the relationship between super domination number and domination number of component of graphs. Now let's look into the basic definition which we require. First is the definition is the open neighbor. Open neighborhood is the set of a graph is the of a vertex in the graph is the set of all vertices adjacent to that vertex, and it is denoted by n of u. And that vertex is said to be a private neighborhood with respect to the complement of that set if the vertices u and v satisfies the condition n of u intersection S bar equal to singleton set V. A set S subset of V is said to be a dominating set if every vertex in S bar has at least one neighbor in S. That is, n of V intersection S bar is not empty for all V belongs to S bar. And if we consider all the dominating sets in G, the least cardinality among all the dominating sets is the domination number gamma of G. Then comes the definition of super dominating set and super domination number. A set which is a subset of V is said to be super dominating if for all V belongs to S bar, S complement, there exists a U belongs to S such that N of U intersection S bar is a single element V. And the minimum cardinality of all super dominating sets is in G is the super domination number. Now let's look in the preliminary results of super domination number, which are for a path graph Pn, where n is greater than or equal to 3, n is greater than or equal to 3, then the super domination will be upper ceiling function n by 2. If there is a complete graph and it's, n is greater than or equal to 2, then the super domination number is n minus 1. For a cycle graph, the super domination number is upper ceiling function n by 2 if it's, and the n is congruent to 0, 3 mod 4. Otherwise, it is n plus 1 upper ceiling function n plus 1 by 2. So if there is a star graph and the n is greater than or equal to 2, the super domination number is n minus 1. These results were there in super domination sets in graph paper. Now let's look into the super domination number of some particular graph. So basically, we have a cycle graph C3, and we can obtain a Helm graph when we add a central vertex and join to the vertex of cycle graph C3. Now we have obtained the Helm graph. So in order to obtain the, this is a wheel graph. In order to get the Helm graph, we need to add pendant edges towards the vertices of the graph C3. Now we have obtained the Helm graph. Now when we join the pendant vertices to the central vertex, we will obtain a flower graph. Now basically, like we will see how we can calculate the super domination number of a flower graph using the example of flower graph FL3. So here the vertices, vertex set is x1, x2, x3, y1, y2, y3, y4. And now we find the neighborhood of the vertices x1, x2, and x3. So we can see that the neighborhood in the all the vertices, the vertex y4 is common as the neighborhood, and corresponding to n of xi, there exists a yi where I equal to 1, 2, and 3. Some of the dominating sets here examples are y4, x1, x2, x3, y1, y2, y3. So we get that the super domination number is 1 because it is the minimum cardinality. And suppose we consider this S equal to x1, x2, x3, and y4 as the set S, we can see that the condition of the super domination number is satisfied. So we can say that it is a super dominating set. So we can get that super domination number of a flower graph FL3 is 4. So flower graph, the basic definition of a flower graph is that it is a graph obtained by joining each pendant vertex to the central vertex of the Helm graph. This is an example of flower graph FL3. So there is a theorem which we have found out that is a flower graph with n greater than or equal to 3 has a super domination number n plus 1. Now let's move into the friendship graph. Friendship graph is actually a graph which is defined as a one-point union of n copies of cycle graph C3. It is denoted by FRN. It is also known as Dutch Minwell graph. Here is an example of friendship graph FR4. So here we will have a central vertex and there will be vertices y1, y2, y3, y4, y5, y6, y7, y8. So we have a theorem that is for n greater than or equal to 3, the super domination number is given by n plus 1. Now let's look into what is comb product of graphs. To understand what is comb product, we need to actually understand what is identifying a vertex to another vertex. Suppose we have a two vertices u and v. Identifying the vertex u to v means that we combine both the vertices to form a single vertex u comma v. Now, then let's look into the definition of comb product. Comb product means that if we consider two connected graphs G and R, and we take the vertex C from the graph R, the comb product between the graph G and R is a graph obtained by taking one copy of the graph G and cardinality V of G copies of the graph R and identifying the jth copy of graph R at vertex C with the jth vertex of G. Now let's see how we can illustrate components. Suppose we have a complete graph K5 with the vertices A, B, C, D, and E. Now suppose we want to adjoin with at the path P2, we will get the graph like this. F, G, H, I, J are the vertices of path P2, and the vertices A, B, C, D, E here are the vertices like obtained after identifying the path P2 with the complete graph K5. So now let's look into the super domination number of components. Some results on super domination of components of graph. First results are that if it G component R is there of two connected graphs, then the super domination number of will be cardinality V of G times super domination number of the second graph. So we can generally, this is a detailed proof. In general, we can say that if we consider two component of super domination of component of two graphs, it will entirely depend on the graph R and the number of vertices in G. So next we have our results again, that if there are two connected graphs G and H, then the result is that one will be 1 less than or equal to domination number of component less than or equal to super domination number of component. Then there are some corollaries, that is super domination number of two paths joined together is m into upper ceiling function of n by 2. And if we take the component of a path graph PM and the cycle graph CN, we have the result that it will be m into upper ceiling function n by 2 if n is congruent to 0, 3 mod 4, and otherwise it is m into upper ceiling function n plus 1 by 2. And if we take the component of a path PM and a complete graph Kn, the result is m into n minus 1. And if we consider the component of cycle graph CM and Cn, we will get that it is m into.
Anjana, please note, it is time up.
Okay, sir, I'll conclude. So similarly, we can obtain the results of cycle graphs together, then cycle and path graph, cycle and complete graph, then two complete graphs together, complete graph and path, and complete graph and cycle graph. So in conclusion, we can say that we analyze certain graphs and obtain the exact value of super domination number and the component of some graphs. The super domination number of components and other graph parameters were also studied in this study. These are my reference. That's it. Thank you.
Any questions? Okay, thank you, Anjana. The next participant is Amarendra Kumar Patnaik, presentation number CO4. Amarendra Kumar, are you ready?
Am I audible? Am I audible, sir?
Hello.
Hello, am I audible, sir?
Yes.
Hello. Am I audible, sir?
Yes.
Can you share mine? Hello.
Yes, you are audible.
Good afternoon, everybody. Respected ma'am and respected sir and my dear colleague. I want to present some one topic, that is study the domains of infinite algorithms of calculation of nilpotent matrix groups. Abstract. We design algorithm for nilpotent groups using the method we describe for computing with matrix groups, defined over a variety of infinite domains. In particular, we present an efficient approach for checking the nilpotency of a matrix group over an infinite field. For a given nilpotent matrix group, we also propose technique that resolve a number of related structure concerns. Keyword: nilpotent, algorithm, matrix group, homomorphism is finite. In introduction, in a very new and underdeveloped area of computational group theory, computing with matrix group over infinite field present quite different obstacles than those encountered when computing with groups over finite fields. One reason that some classes of matrix group over finite field make it impossible to solve even the most fundamental computational tasks such as membership checking and conjugacy problem. Matrix entry growth is one example of a kind of a serious complexity problem that can occur. For any category of groups, finiteness of proofs are a fundamental computational problem. As a matter of course, it is possible that finiteness cannot be decided in general. For matrix group, though things seem better, keep in mind that the integral domain R F generated by the entries of elements of S. S1 is the definition space for a matrix group given by a finite set S of generators over a field F. For this reason, it is sufficient to build algorithm just for the field F is equal to P of x1, x2, xm, where xi are the independent indeterminates, m is equal to 0, and p is the either number field or finite field. Both deterministic and random techniques have been devised by the different authors to determine whether or not given matrix group over Q is finite. Finiteness testing over any number field is now possible with the use of this technique, and the standard reduction delivered by modeling algebraic numbers as matrices over Q. However, this strategy can only go so far because increase the matrix degree is a time-consuming and resource-intensive process. For deciding finiteness group over functional fields are studied. The importance of computational in matrix algebra is a recurring issue in these articles. Both deterministic and random techniques have been devised by different authors. Algorithms in polynomial time have been presented in both zero and positive characteristics, although their usefulness is constant. Not only are there no public implementation, but there are none available either. A method for determining whether or not a set is finite differs fundamentally from previous approach by shifting the ground domain using congruence homomorphism. The method is generic and applicable across all domains. With the same implementation, a method was applied to the problem of determining whether or not given matrix group is nilpotent. The Nilmat gap package contains an implementation of algorithm from the effectiveness of a Nilmat algorithm is the testing finiteness of a nilpotent matrix group over Q at very large degree. Where other known technique fails has been demonstrated experimentally. This research utilized the method to create workable methods for determining the finiteness of a matrix groups over functional field. The changing ground domains via congruence homomorphism lemma. So we will say that is a unique factorization domain. Q is irreducible and is the primarily ideal Q of, let's pretend that the torsion element of a G of n delta rho are not all 0. If Z is a set, then there exists a prime P such that P, to put it another way, P PB is equal to summation of I is equal to 2 to P by I, Q to the power I minus 1, B to the power I. For some B belongs to met of n comma delta, and each torsional component of G of n comma delta comma rho has a P power order. Proof: H belongs to G of rho, G rho have a prime order P. We get H1 n plus Q B for some B belongs to met of n comma delta. Then 1n is equal to h to the power p, and 1n plus pqb plus p by I, g to the power I, p to the power I plus dot q to the power p, b to the power p. The binomial coefficient has interpreted a module character. Hence, pb is equal to minus I to the power I to p by I, q to the power I minus 1, b to the power I. Thus, either q divides p or q divides each element of a B. Hypothetically, let's say Q does not split P. As a result, alpha greater than 1, Q to the power alpha for some positive integer 1. Q divides each element of a P, while Q to the power alpha plus 1 does not. However, it implies that Q to the power alpha plus 2, Q to the power 2 alpha plus 1 divides PB, which is obviously false. That's why Q is a divisor of a P. Hence, an element of prime order R is not equal to P if and only it contains a non-trivial element of a P order. Therefore, 1 is equal to Px plus Ry for some x, y belongs to Z is divisible by Q. Similarly, now another also proposition in same way. Now methods of infiniting groups of non-negative potential matrix element. Nilpotent linear groups can be divided in general group theory. We frequently apply this technique of reducing to simplest possible case. Nilpotent linear groups have an easier time with this reduction than arbitrarily linear groups do. In this section, we will think about the computational method for accomplishing the reduction. Similarly, some lemma is given. Now, deciding finiteness. After verifying that G is less than or equal to GL n comma f is nilpotent, we can move on to more elementary computational issue for G, such as checking whether G is finite or not. Various writers have addressed how to decide whether or not a matrix group over an algebraic number, field or functional field is finite, and Bills has published a practical implementation of idea gap for groups over Q. In this section, we offer ground field independent, generalized method for determining finiteness. Here, Sedgberg, where it fits. Each finite generator linear group G has a normal subgroup and with a finite index and a finite order element that all unipotent. In particular, G that torsion 3 by finite if and only if the character f equals to 0. For maximum in R, we refer to rho to it as a SW homomorphism. If and only n is a congruent subgroup of a 0, the value n as a 0 is not produced in the proof of Selberg-Weppres theorem. It's finite S. That means is finite taking input will be finite subset of S of GL and R. R is a character vector with least significant R is equal to P, which is greater than or equal to 0. The output will be the true if and only G is equal to S is finite. And otherwise,
Excuse me, sir.
Yes, sir.
Your time up.
Yes, sir. I will come. Now, in conclusion, in addition to this primary function, Nilmat also has tools for determining whether or not a group is finite. Computing the order of the finite nilpotent group, locating the Salus system of nilpotent group over a finite field, and determining whether or not the group is totally reducible. Nilmat also includes a collection of primitive groups that are nilpotent over finite field. Because of the significance of nilpotency in group theory, checking for it is a fundamental feature of any computational group theory system. Here, we offer the first general and efficient method for working with the infinite nilpotent matrix group in computation. Some of the nilpotent testing method in gap and magma helps to decide nilpotence even for an finite matrix group, and depth helps for practically all infinite matrix group. To address this issue, we implemented our algorithm as part of the gap package nilpotent across finite fields and Q. Since then, we have achieved significant advancement, especially concerning the finite soluble. So these are this is my references. Thank you.
Any queries or doubts from the participants? Thank you, sir. The next participant is P. Monisha. Presentation number CO5. Monisha, ma'am, are you ready? Monisha, ma'am. I repeat, presentation number CO5, P. Monisha. Okay, then we are going to the next paper, Rija SB. The presentation number is CO6. Rija, are you ready?
I'm ready, sir.
Could you share the screen?
Good evening, all. I'm Rija, Research Scholar, Department of Mathematics, University College. I am presenting on the topic on the core and non-core vertices of singular graphs. Introduction. Definition of adjacency matrix. Adjacency matrix A equal to AIG of a graph G with n vertices V1, V2, etc. Vn is a n square matrix with n raised AIG equal to 1 if Vi and Vj are adjacent and AIG equal to 0 otherwise. Definition. Definition of a singular graph. A singular graph is a graph with a nullity of its adjacency matrix greater than 0. Otherwise, the graph is called a non-singular. Definition of kernel eigenvector. In a singular graph, the system of linear equation Ax equals 0 has infinite number of solutions, where vector x equal to xv1, xv2, etc. xvn transpose. Non-zero solution of Ax equals 0 is called a kernel eigenvector of G. Definition of kernel eigenspace. Collection of all kernel eigenvectors of G, including 0 vector, is called the kernel eigenspace of G. Consider this figure. This graph is a singular graph with a nullity 2. Kernel eigenvectors are -1 vector -1 1 0 1 0 transpose, 0 vector 0 -1 0 1 transpose, vector -1 -1 1 1 transpose, etc. Core and non-core vertices of singular graphs. Core vertices and non-core vertices of a singular graph with nullity 1 are defined in the reference coalesced and embedded net graph within singular graphs by ICMICDS-22. Here we extend the definition to singular graph with a nullity greater than 1. Definition. Let G be a singular graph with the n vertices V1, V2, etc. Vn and nullity eta greater than or equal to 1 and B be a basis of its kernel eigenspace. If vertices in G are relabeled in such a way that all the vectors in V are of the form vector x equal to transpose of the vector xv1, xv2, etc. xvm, 0, 0, etc. 0, where xv1, xv2, etc., xvm are non-zero in at least one kernel eigenvector in B, then the vertices v1, v2, etc., vm are called core vertices, and the vm plus 1, vm plus 2, etc., vn are called non-core vertices. If we consider this graph, consider the singular graph G in figure 2. Eigenvalues of G are 0 with the multiplicity 3, minus root of 5 plus root of 13 by 2, minus root of 5 minus root of 13 by 2, root of 5 plus root of 13 by 2, and root of 5 minus root of 13 by 2. Here, graph G is singular with a nullity 3. Basis of the kernel eigenspace of G is set of 3 vectors, minus 1, 1, 0, 0, 0, 0, 0 transpose, commas 1, 0, minus 1, 0, 0, 0, 0 transpose, and vector minus 1, 0, 0, 1, 0, 0, 0 transpose. Since xv1, xv2, xv3, xv4 are non-zero in at least one kernel eigenvectors in B, the vertices v1, v2, v3, v4 are called the core vertices. In all the kernel eigenvectors in B, xv5 0, xv6 is 0, and xv7 is 0. So v5, v6, v7 are called the non-core vertices. This from figure 2, we can observe the following. v7 is a pendant vertex and its neighbor v6 is a non-core vertex. And second observation, the vertex v1 or v2 or v3 or v4 has only two neighbors, v5 and v6. v6 is a non-core, so v5 is a non-core vertex. Third observation, all neighbors of v5 are the neighbors of v6, and the v6 has only one neighbor, v7, not adjacent to v5. The vertex v7 is a non-core vertex. This observation leads to the following theorem. Let G be a singular graph with a nullity greater than or equal to 1. A, the neighbor of a pendant vertex is always non-core vertex. If there exists a vertex of degree k greater than or equal to 2, such that its k minus 1 neighbors are non-core vertices, then its other neighbor will be non-core. C, if there exist two vertices v and v dash such that all neighbors of v are the neighbors of v dash and v dash has only one neighbor, v double dash, not adjacent to v, then v double dash will be a non-core vertex. Example, consider the singular graph in figure 3. In G, all core vertices in the set of all neighbors of V4 are the neighbors of V3. And V3 has only one neighbor, V5, not adjacent to V4. Hence, V5 is a non-core vertex. Example, consider the singular graph in figure 4. In G, all neighbors of V1 are the neighbors of V8, and all neighbors of V2 are the neighbors of V8, and V8 has only one neighbor, V9, not adjacent to both V1 and V2. And also, V1 and V2 do not have a common neighbors. Hence, V9 is a non-core vertex. This observation from above given two examples leads to the following theorem. Let G be a singular graph with the n vertices v1, v2, etc., vn, and a nullity eta greater than or equal to 1, and A be its adjacency matrix. A, if there exist two vertices vi and vj such that all core vertices in the set of all neighbors of vertex vi are the neighbors of vj, and vj has only one neighbor, vl, not adjacent to vi, then vl will be a non-core vertex. B, if vi is the only neighbor of the neighbors of v1, v2, etc., vk, and if v1, v2, etc., vk do not have common neighbors, and vj is the only one neighbor of vi, not adjacent to v1, v2, etc., vk, then vj is a non-core vertex. Consider the graph. Example, consider the singular graph G in figure 5. In G, the vertices V1, V2, V3 have only two neighbors, V4 and V5, and the vertices V4 and V5 are adjacent with the degree 4. Here, V4 and V5 are non-core vertices, and V1, V2, V3 are core vertices. Theorem. Let G be a singular graph with the n vertices V1, V2, etc. Vn and nullity eta greater than or equal to 1. If the vertices V1, V2, etc. Vn minus 2 have only two neighbors Vn and Vn minus 1, and the vertices Vn, Vn minus 1 are adjacent with the degree n plus 1, then Vn and Vn minus 1 are non-core vertices, and V1, V2, etc. Vn minus 2 are core vertices. Conclusion. We have developed some techniques for identifying core and non-core vertices of singular graphs. The nature of vertices in any singular graphs can be identified by applying the combination of these techniques. Further study is needed in this area to develop more techniques for the identification of nature of vertices in singular graphs. These are the references.
Audience part. Thank you, Rija. Next, the last contestant, P. Monisha, paper presentation number CO5. Monisha. Monisha, are you audible?
Sir, am I audible?
Okay, we can start the presentation,
Sir,
right?
am I audible?
Yes. Please start the presentation.
Started. Sir,
We can start the presentation. Am I audible?
yes, sir.
Okay. You start.
Sir, screen is visible.
Yes.
So, good evening, everyone. I am Monisha, full resource scholar, Department of Mathematics, SRM Institute of Science and Technology, Ramapuram. I am doing my research work under the guidance of Dr. Sindhu Devi ma'am. So, title of patient stability analysis and backward bifurcation of malaria model. So these are the content of my presentation: abstract, introduction, fuzzy SAR model, stability analysis, backward bifurcation, fuzzy control system, conclusion, and reference. Abstract. In this paper, we examined a fuzzy SAR model for transmission, malaria transmission to find stability analysis and fuzzy basic question of the virus transmit to, and also find two equally. The model used to examine or dynamic system, and the results show that the backward bifurcation occurs for the certain values. So introductions. Malaria is one of the oldest disease study in mathematical approach. It is one of the health problem. It is one of the health problem across the world. Every year, 250 million people become infected in malaria. 2022 World Health Organization estimate that 251 million people become infected in malaria and 6,07,000 died for malaria in 85 countries. So in 2014, Raymond Unclove, we have discussed the phenomena of backward bifurcation does not arise depending on vaccinations, coverage, and efficiency of vaccines. So in 2020, Kaiming B et al., we have stability and backward bifurcation by changing the population system to an open population system. Computational results suggest continuous optimal complications. So in this paper, we main probability analysis and backward bifurcation to study the fuzzy SAR model area. So for next one, fuzzy SAR model. The model is defined by spread of malaria disease. So first three represented total populations of people, and the last two equations represented the total populations of mosquito. So SP is a susceptible of people, IP is a infected of
SM is
and SM is a infected of mosquito, and IM is a SM is a susceptible of mosquito and infected of mosquito. So UP, UM, and mu P, mu M, P, sigma M, beta P, beta M, gamma P, delta P. These are the fuzzy parameters. So mu P is the requirement rate of people. U is the requirement rate of mosquito. So sigma P is a natural death rate of people, and sigma M is a natural death rate of mosquito. So beta P is a transmission rate of people, and beta M is a transmission rate of mosquito. Epsilon P is a loss of immunity rate in people. So gamma P is a recovery rate of people. Del P is the rate of people in disease of malaria. So next we have for stability analysis. To first we have find equilibrium points and basic reproduction numbers are two equilibrium points. One is disease-free equilibrium, other is endemic equilibrium. So the disease-free equilibrium, only one value means infected recovery value is 0, susceptible values exist. Endemic equilibrium, all values exist. So that means susceptible, infected, recovery, all values are exist. Theorem 1 represented, theorem 1, theorem 2 represented the local stability of our disease-free equilibrium, disease-free and endemic equilibrium points. Theorem 1 represented R0 less than 1. This is locally asymptotically stable. So the value R0 greater than 1, the point is stable. Theorem 2 represented the R0 greater than locally asymptotical. Suppose R0 less than 1 values exist, the point will be unstable. So backward bifurcation, in this case, we found the derivative of the condition for backward by using Central-Malford theorem. So here, once again, we have our model consider F1, F2, F3, F1, F2, F3, F4, F5, equation 2. So next two, we have to explore possibility of backward bifurcation at R. We have take the base reproduction number equal to 1. So we have considered the transmission rate, the transmission rate beta B bifurcation parameters. So by using Jacobian matrix to solve the backward bifurcations of center manifold theorem. So this slide represented the backward by this represented the equation 4 represented matrix of right eigenvectors. Equation 5 represented the Jacobian matrix of left eigenvectors. So we use the property of A dot B equal to 1, A1, A2, A3, A4, A5. These all values of equation to solve the equation 4 and B1, B4, B5. These values are to solve equation 5. So from the conditions of from the formula of theta and psi, so finally the result come positive and the backward parameter greater than 1, so the backward bifurcation is exist. So next one, fuzzy control system. In these sections we are using control system of the disease of malaria by using fuzzy base number and bifurcation parameters. So first case, the load is low, so the disease transmissions will be weak. So to conclude, the disease will be easy to control. So the second, the virus load is medium, so the disease transmission will be medium of infections. So that means either extend or not speed faster. So the third condition, the virus load long, the disease transmission will be high amount of infection rate. So that means the spreading is faster. So conclusions, analyzing as on a non-linear mathematical model of malaria transmission. So we have a local stability of our models, endemic and equilibrium. Our main goal of this model is to highlight of bifurcations. The backward bifurcation result may be useful in understanding of disease spread of malaria. So the reference of my presentation. Thank you, sir.
Any queries from the audience part? Thank you, Monisha.
Thank you, sir.
That was the last paper in the first contributory session. Thank you all the candidates for the nice presentation and all other participants. Today, we conclude day 1 session of the conference. Tomorrow, day 2 session will start at 9:15 a.m. with tutorial sessions. Thank you.